Hello and welcome to this episode of Physical Attraction series on cosmology, and we've got another great title for you today. This is Cosmological Eggs and the Edge of the Universe. So let's get into it. In the last few episodes, we've discussed how the theoretical formulation of cosmology that arose from Einstein's theory of general relativity gave rise ultimately to simple equations that dictated how space-time itself might behave under the influence of gravity and other forces. And we've discussed how this theory was combined with Hubble's observations in the 1920s that far-off galaxies appeared to be receding at a rate proportional to their distance, to determine that the true cosmology of the universe was not in fact static, but that the universe was instead expanding over time. Just because there was this new theory that the universe was expanding over time, though, did not mean it was universally accepted. Part of this was a significant measurement problem in the early days. The Hubble constant tells us the rate at which the universe is expanding. It's that constant of proportionality between the distances of far-off galaxies and the apparent speed they're receding at. You can use this to establish an estimate for the age of the universe. If we assume that the rate of the expansion has always been constant, we can argue that at one point all of the matter that now makes up the stars and galaxies was located at exactly the same position. We then know that if the distance between these stars and galaxies is distance d today, and the rate of expansion is constant, then d must be the distance travelled due to moving at this Hubble speed for a time t, where t is the age of the universe at the time. So we also know that the speed is v equals h naught d. So we have d, the average separation between galaxies, as t times h naught times d, which is the speed, and therefore t, the age of the universe, is approximately 1 over h naught. In other words, the reciprocal of the Hubble constant gives us an estimate for the age of the universe. This reciprocal of the Hubble parameter, by the way, is sometimes called the Hubble time. It's kind of a characteristic timescale for the age of the universe. And this makes some sense. A universe that's been expanding more quickly would be younger, but it would still look the same, while a universe that is expanding slowly would actually be older because the distances between the galaxies would be the same, but it's been expanding more slowly. Sadly, this simple equation is far from the whole of the story, as we'll see later on. For example, in a universe with matter that has a gravitational influence, the kind of Einstein cosmology we've been talking about is going to slow down the rate at which that universe expands. Consequently, the universe was once expanding at a much faster rate than it is today. In such a universe, its expansion is now slower than it was before. This means that the Hubble constant used to be bigger in such a universe, and therefore the age of the universe is actually less than the Hubble time. Perhaps between 66 and 90% of the Hubble time, depending on how much matter you think is in the universe. So calling it a Hubble constant is quite misleading, and often people say Hubble parameter instead. But in the 1930s and the 1940s, far from fitting together nicely, the link between the Hubble constant and the age of the universe created a contradiction. Due to incorrect measurements of the Hubble constant at the time, these estimates only gave an idea for the age of the universe at around 2 billion years. But this was a serious problem. Studies of the relative abundances of radioactive elements which decay with a given time period, basically carbon dating for the Earth but using uranium which has a much longer half-life so you can use it to measure much bigger distances in time, this had shown that the Earth itself must be substantially older than 2 billion years. Obviously, having a situation where the Earth is older than the universe was a pretty awful contradiction for the new cosmology to try and resolve. It would take until the 1950s for the major errors that Hubble had made to actually be uncovered and explain what was going on. So there are a few errors here. One was in classifying stars, including failing to understand that there are two types of the Cepheid variable stars, which were used at the time as standard candles to measure distances in the universe. After these sort of errors were corrected, the Hubble parameter started to be measured at something closer to its true value today, which is around 70 kilometers per second per megaparsec. With this correct value, the age of the universe suddenly expands to be closer to 14 billion years, which is much nearer to the currently accepted value. Paradoxes surrounding the age of the universe, though, would continue to bedevil cosmology right up until the 1990s. And there are still debates in 2020 about the precise value of the Hubble constant, and whether new physics is needed to explain the difference between different ways of measuring it. So in some ways the debate still goes on. The reason I mention this misunderstanding is to point out that the idea of an expanding universe didn't suddenly become universally accepted. There were still contradictions in this theory to work out, and confusion and consternation as to what would eventually be accepted as true. This explains why the steady-state theories of the universe were still popular quite a long time after Hubble's observations, and the theoretical cosmology of Einstein, Friedmann, Lemaitre, etc. Even at this stage, after Hubble's observations and Einstein's theories, it was nowhere near a done deal. But as soon as cosmologists had had at least this idea that the universe was expanding, the question immediately became, okay, expanding from what? If the universe isn't static and eternal but actually evolves with time, then what has it evolved from and what is it evolving into? Lemaitre came up with one of the first theories. He suggested that perhaps the universe had once been concentrated into the space of a primordial atom. This atom would have been like a huge atomic nucleus all packed together tightly, and would gradually have decayed and subdivided, in a process similar to radioactive decay, shooting off fragments that would eventually become stars and galaxies. If you concentrated all of the known matter in the universe into densities similar to that of a nucleus, you'd end up with something about 30 times the diameter of the Sun, perhaps about the size of the solar system out to Earth, as one big atomic nucleus. He published this theory in a book of 1946 called The Hypothesis of the Primal Atom. Now this theory, where you start with a big cosmological egg that's shooting off all sorts of different matter, kind of sounds absurd to a modern-day physicist's ear, but there are some pleasing aspects to it. In a sense, you have a kind of unification of the forces at the start of time, where the strong nuclear force, which deals with individual nuclei, is balanced against the gravitational collapse of all matter in the universe. There's a nice element in it which reflects some old creation myths, such as the Viking idea that the universe is composed from the body of a giant. Indeed, Lemaitre himself referred to it as a cosmic egg, which sounds very mythical indeed. And of course, it's not too dissimilar from an idea that was quite popular later on, that the universe began as a singularity like a black hole, once you have a theory that allows matter to collapse even further than the density of a nucleus. This theory, of course, owes much to the work of Stephen Hawking. Of course, all of these theories were running into difficulties due to the age of the universe paradox. Lemaitre pointed out that, given how much freedom you had in adding a cosmological constant to Einstein's theory, you could actually have a situation where the universe began expanding rapidly, then stopped, hovering at a particular size for a while, before the expansion started again. From this, you can basically reconcile your cosmological model with any age of the universe that you like, because you don't know how long it hovered at that particular size. But of course, it's even more unsatisfying if you need a really bespoke cosmological constant to explain your age of the universe. One interesting twist in history that arose here was that Einstein actually developed another model of cosmology during this time. This happened in 1931, but the paper itself was never published, and its significance was only really noticed by some researchers from Waterford in Ireland back in 2014. In this paper, Einstein was still trying to see if there could be a model of the universe that didn't change, or at least whose appearance didn't seem to change, with the passage of time. He ended up coming quite close to the steady-state model that Fred Hoyle would later come up with, which takes us right back to where we originally began this series, with his somewhat derisive coining of the Big Bang Theory, and his argument that it was incorrect. The idea behind this theory is that as the universe expands, more and more matter is created, keeping the density of the universe as a whole constant. As galaxies are taken away from view by the expansion of the universe, whisked away from the horizon that we can see, new matter is created, generated in space, and new stars and galaxies form from this matter to take their place. In this way, we still have our nice cosmological principle. The universe, on average, always looks similar even as it expands. This way, as long as the continuous creation of matter is occurring throughout space, you can have a universe where space-time is expanding and things generally continue to look the same, without appealing to any time in the distant past when everything was clustered together in a single point. Instead, you have an infinite universe with infinite matter generation, and galaxies and stars being whisked off the horizon and being created to take their place again. And you have no reason to suspect that there was ever a point when this began, so to speak. This, of course, helps resolve an issue with the universe that arises due to an idea of an expanding universe and Hubble's law. We previously talked about Olber's paradox. If the universe was infinite and static, why isn't the night sky white, with far-off stars having an infinite amount of time to radiate their light towards us from all directions? With an expanding universe, we have a different view. As galaxies recede from us, the speed at which they're apparently receding gets faster. Over time, the furthest galaxies will appear to be accelerating away from us due to this expansion of space. Now, beyond a certain distance, the apparent speed of these galaxies away from us will be faster than the speed of light. And of course, you can even figure out what this distance is. We know that v equals h0 times d. It just needs to be a sufficiently large distance d that when you multiply it by the Hubble constant, you get a speed, an apparent speed, faster than light. This doesn't violate special relativity, which you'll remember sets a speed limit for the universe that is the speed of light. Nothing is actually moving at speeds even close to the speed of light, or faster than it, so to speak. These are instead just apparent velocities caused by the rate at which the distance between us is getting bigger. It might help to imagine it from the perspective of a single photon of light in the far-off galaxy that's emitted and travels towards our solar system. Sure, it's travelling, but the distance between us and the photon is expanding all the time. If that total distance is expanding faster than the speed of light, there's no way the photon can possibly catch up and reach us because the light speed limit is absolute. So instead it will just find that the distance between it and its final destination with us, which it will never reach, is constantly expanding, and it's expanding faster than it can travel. So if you don't have a steady-state theory like Einstein's, where matter is continually generated, and you don't have a cosmology where the expansion of the universe slows down over time, perhaps due to the gravitational influence of matter pulling it back down again, then you actually have what seems to be a pretty alarming situation. As every distance in the universe expands and far-off objects move away from us at a greater rate, they end up being whisked over this distance horizon. Now, you might initially think of the horizon as being exactly where h0d is equal to the speed of light. It's not actually, because of the vagaries of how the universe expands, but I won't go into that in too much detail at the moment. We can actually see some objects that are moving away from us faster than the speed of light right now, because what matters is the distance that they've had to travel, and due to the changing rate of the expansion of the universe, that distance might not actually be greater than the speed of light multiplied by the Hubble constant today. But that is a pretty decent estimation of how far away this horizon might be. You do need a more detailed model of how the universe has expanded historically to figure out exactly where this horizon is. But there is a horizon, and once things get whisked over that horizon by the expansion of space and time, it's impossible for light from those distant objects to reach us anymore. Any photon finds itself on a journey to us whose length expands faster than it can travel. It's unreachable. It's climbing up the down escalator. It will never get there. It reminds me of that quote from Galliano that old listeners will remember. Quote, "Utopia is on the horizon. I move 2 steps closer, it moves 2 steps further away. I walk another 10 steps and the horizon runs 10 steps further away. As much as I may walk, I'll never reach it. So what's the point of utopia? The point is this, to keep walking." There is no way for information about what's beyond this horizon to ever reach us. The photons will be setting out on impossible journeys. So we have this concept of a cosmological horizon. As to whether utopia is beyond it, well, it's probably just more stars and galaxies that look quite similar to the ones around us now, but the point is that we can't ever know for sure. There are actually several different horizons for the universe, depending on how you want to look at it. I have to admit, when I first studied cosmology as an undergrad, it was the distinction between all these different types of horizon and what they meant that probably confused me the most out of everything. And that was 5 years ago now, so if my explanation is a little mangled, I can only apologise. But before we get into the taxonomy of horizons, we should reflect a little on what this means. First of all, we can only ever see a certain sphere of the universe, the observable universe, and it will be very difficult for us to ever infer what's going on outside of that particular sphere. For all we know, it could be quite a lot larger than the parts of the universe that we can see. So, perhaps frustratingly, it almost doesn't make sense to talk about the universe having an edge, or what it's expanding into, because we'll never really know where the edge is beyond the edge of what we can observe. Now, we know how the edge of what we can observe is changing over time, because that's about how long light has had to reach us. But we don't know what's beyond that. Secondly, we should appreciate what our current view of cosmology means, because we're actually in a very special era in the history of the universe. All of the distances between galaxies are expanding. Eventually, if expansion continues, these distances are going to be large enough that light is not going to be able to cross them. After all you need is for a given distance to be expanding at a rate faster than 1 light year per year, and light's not going to be able to traverse that distance. At this point then, when all of these distances have expanded, and the distances between galaxies on average is longer than this observable horizon, galaxies will become cosmically isolated. It will be impossible, or at least I can't really see how it would happen, for those in one galaxy to infer that another galaxy ever existed. Once we've got there, then the old models of the universe developed by Herschel and so on that we described in earlier episodes, where the Milky Way is the only galaxy, would actually look like our universe, at least the observable part of it. According to our best calculations, around 100 billion years from now, all of the galaxies outside of the Milky Way's local group will have been removed from our observable universe. We'll only be able to see, from our perspective in the Milky Way, other galaxies in that group. If there were astronomers on Earth, having forgotten everything that we knew, if Earth is still there, that is to say, if there are astronomers within the Milky Way who are observing things outside of our galaxy, they would only see these other galaxies and not other groups, so there would be no knowledge of galaxy groups that anyone could find out about. Perhaps a few 100 billion years later, all of the galaxies in the local group are expected to coalesce into a single galaxy. At this point then, we won't be able to observe any other galaxy in the entire observable universe, just one supergalaxy made up of the local group. I would say here that I don't want to go off on one, but actually I totally do, because there are other theories which suggest that actually the peak habitability in the universe is going to be at a time that is much, much later than this. In other words, the universe will be most hospitable to life in the far-flung future, basically because you have a lot of low-mass stars and planets in the Goldilocks zone, where the type of chemistry that we think is conducive to life can occur. So consider it if this is true. By the time the universe is most suitable for life, these distances will be too large to see across. Every gravitationally bound object is going to be totally isolated at some point. What would cosmology look like to civilizations that evolved under these conditions? They might only speculate that such things as other galaxies ever existed beyond the universe's horizon. There would be no way of knowing for sure. Who knows, they might never even discover things like the redshift because there would be nothing to see at large distances. We only know the universe is expanding because we can see other galaxies at distances of many megaparsecs away, which are being redshifted by the universe's expansion. But they wouldn't see that at all, because all they have is just a small, quite compact galaxy in the centre of an apparently endless void, with the other isolated supergalaxies somewhere beyond that infinite horizon. Cosmology would be a lot more boring a field to study to such a future civilization. All of that information about the universe's large-scale structure would be lost, unobtainable. Perhaps they would then be unable, except through really precision measurements of these empty spaces or within their own galaxy, to infer the age of the universe at all. And if this is all accurate, then you have to appreciate in a way that maybe we're quite lucky to exist in the brief window of time, the first few 100 billion years, perhaps amongst the first few civilizations that could exist in the universe, to be able to observe other galaxies beyond our own, to make all of these inferences about the long ago past and the far future, before it all slides out of view and becomes unknowable in the distant future. How strange it is to be in a position to know and find out all of these remarkable things. How strange it is to be anything at all. So let's briefly discuss then, as promised, these different horizons, these different means of determining the edge of the universe. First we have the Hubble horizon. This is the distance at which apparent recession velocity from us is the speed of light. This is basically the length scale that's set by the speed of light divided by the Hubble constant. Objects beyond this distance will be receding from us at a rate faster than the speed of light. but we might still be able to see them, because light from these objects from the past is still reaching us and will do so for some time if they've just slipped over the horizon. You can think about some of those photons that made it halfway through their journey and therefore just had enough time to get over the visible horizon before we could get away, even though the object itself right now, the photons that it's emitting right this second, will not actually reach us. It's only as they exist now, which could be billions of years after the light we'd see from them anyway, that we can't see them anymore. Then we have the true cosmological horizon, which is sometimes called the particle horizon. This is the maximum distance at which light could possibly have reached us in the entire age of the universe, taking into account its expansion. And this is what defines the actual size of the observable universe, so it includes all of the photons that will ever reach us. Technically speaking, you can define something called the conformal time, which is the length of the cosmological horizon divided by the speed of light. To actually get this real particle horizon, you need to integrate over the different rates of expansion of the universe for all time. Depending on your precise model of the universe, this distance is going to be changing as well. Our current best understanding suggests that the cosmological horizon is about 46.9 billion light years away. So it is actually more than 3 times the simple speed of light times age of the universe horizon that you might come up with. This is the furthest region from which information can possibly reach us. Owing to the expansion of the universe, there are obviously places towards the edge of this where any light that's emitted today will never reach us, but we can still see light from the past. This, of course, gives rise to another horizon, which is the cosmological event horizon. And this is essentially the horizon where we can actually influence things, and where light that's emitted today can reach us from. So in other words, this is the furthest distance that light that we emit today can ever reach the observer in the future, even if we give it infinite time to get there, owing to the expansion of the universe. Because no signal can travel faster than light, this kind of defines the region of space and time that we can actually possibly influence with anything that we do today. This horizon is about 16 billion light years away from us at present. So again, the cosmological horizon is 47 billion light years away, and the event horizon is 16 billion light years away. So there's actually a good 31 billion light years of space, of radius out there in space, that we can still see and still observe, but light from us will never be able to reach it. And we'll never see it as it is today, because it's already slipped over the event horizon, where signals emitted today can reach us from. I did warn you that these different horizons were confusing. Perhaps this is part of the reason why a static universe, where there are horizons but they don't really matter, because new stars and galaxies are always being created to keep everything looking the same, is preferable to some cosmologists. With this discussion of horizons receding back over our horizon, then, let's return to some of the speculations about cosmology in the 1930s. We've discussed how Friedmann's equations gave rise to a solution with a flat universe that was at just the right critical density to expand forever without contracting or eventually accelerating into oblivion. This was the model that Einstein and de Sitter ended up favouring in their model of 1932. Now, the actual density of the universe, as it was measured, as people were trying to figure out how much matter there was in the universe, didn't actually back this up at the time, but it was pretty close. The observed density of the universe seemed to be about 1/10 of the density that would be required for the universe to be flat if it existed. To the physicists of the day, it seemed more likely that the true value was not 1/10 but 1, and the universe genuinely was flat, and that they had just failed to observe all of the matter. After all, there was nothing that would stop it from being a millionth, a billionth, or a trillionth if they were really that far wrong. In astrophysics, 0.1 is suspiciously close enough to 1 to be convinced that you've made an error somewhere. Perhaps some of the matter was not visible, or not easy to see in the form of dust between galaxies or something similar. And this can start to give rise to the idea that the universe is filled with dark matter. Matter that we can't see, but which we can infer that it exists through how it influences structures at large and the universe at large through its force of gravity. It is also worth pointing out that looking at the universe in terms of this critical density does again show you why there were still considerable disputes between the steady-state model of the universe proposed by Hoyle, even after the expansion of the universe had been discovered. This critical density, after all, was just one hydrogen atom in every 1,000 litres of space. To maintain the critical density of the universe as the universe expands then, through this spontaneous creation of matter, you might only need a few hydrogen atoms to be created in quite rare events surrounding the universe, filling in the gaps as the universe expands. Since the rate of creation didn't need to be that high, it might be possible for this spontaneous generation of matter to go unnoticed in our laboratory experiments on Earth, and impossible to really observe in our telescopes given how small the rate of creation of new matter would be. As Fred Hoyle would point out to his critics, if you believe in the competing Big Bang theory, then you have to believe that all of the matter in the universe was spontaneously created somehow at the beginning, rather than that there is some ongoing process that occasionally creates a new hydrogen atom somewhere, which eventually gets built into the stars and galaxies that we see around us. And to him at least, there wasn't really any reason why one of these things was more plausible than the other. So as we move towards the era when Hoyle was proclaiming that the steady-state theory had won over the expanding universe theory, there are really three major pillars that are keeping that steady-state theory alive. One is the ongoing dispute surrounding the age of the universe in the Big Bang theory, and the contradictions between estimates for this age and estimates for the age of the Earth, or the age of stars. One is the fact that it's very difficult to disprove the idea that a few bits of matter might be created spontaneously in the universe round and about the place. It's very hard to disprove the spontaneous generation theory. And thirdly and finally, problems that the Big Bang theory had in explaining how everything was at the very beginning, and the initial spark that might have set it all off, meant that this theory still felt incomplete, compared to an apparently simpler model of the universe, where there was no unexplained beginning, no timescale to worry about, and just an eternal process of gradual creation somewhere that was giving rise to the stars and galaxies as we see them in a kind of eternal way. In the next few episodes then, we'll be discussing the dispute between the steady-state theories and the Big Bang theories in more detail, including how scientists attempted to resolve this dispute throughout the 1940s, 1950s and 1960s. And so this is coming on to the era where we started our first episode with that old radio broadcast that first coined the term the Big Bang. Thank you for listening to this episode of Physical Attraction. You can find us on the web at physicspodcast.com. There you will find the contact form. You can get in touch with us with any comments, questions or concerns that you have about the show, anything you'd like explained, anything you'd like me to talk more about, anything you'd like me to talk less about. Please do get in touch there. I try and respond to all of the different emails I get. You can engage with us on a plethora of different social media platforms. We're on Twitter at PhysicsPod. We're on Facebook, Physical Attraction. You can find the Science Podcast group on Facebook. You can find our subreddit, which is reddit.com/r/physicspodcast. The creators of the theme music for this show are Melody Sheep, and you can support them on Patreon. You can also support us on Patreon, patreon.com/physicalattraction, where you'll find access to lots of episodes early and also some bonus episodes that are only available to subscribers. For example, you'll find the recent bonus episode which we released on Dirac's large number hypothesis, which is an attempt to explain how some of these constants that seem to be hardwired into the fabric of the universe actually got there. You can also support us via the PayPal link, which is on the Physics Podcast website. Any little helps us to maintain the show, pay for hosting costs and so on. Of course, another great way you can help us out is by leaving a review on your podcast platform of choice, or by telling people who might be interested in the show to please give it a listen. All of that stuff is greatly appreciated. I really, really love to see it. It makes me very happy, so if you want to do that and help support the show, please do that. Until next time then, please do take care.